My name is Michael. I work for the German Aerospace Center, and we are a group working on computational electrochemistry. And today I want to give some insights on our work within equality on applying quantum computing to continuum simulation of transport as it emerges in electrochemical cells. So just to give a brief introduction on how our work fits into the equality ecosystem. So our topics are the solution of partial differential equations with quantum computers. For this, we've been working together with Pascal. So we've been using their library, which includes physics-informed neural networks, short pins, and differentiable quantum circuits, short DQCs. And if you're interested in those, they were introduced in the first webinar of the series. Now, our task as an application partner was to apply these to the differential equations that we find in our electrochemical systems. And the reason why we do this is because we see potential benefits in the scaling and resolution in solving these PDEs. And this was also highlighted in the second webinar by our colleagues from Airbus. So we want to talk about electrochemical cells. And if you look at them from the outside, what you usually see is just the anode and the cathode. And you can extract electrical current from there in the form of electrons. However, we are interested in what happens inside these cells. So in this talk, I will focus on batteries. However, the principles that we discuss here are the same for fuel cells. So they also translate to this case. So what we are interested most in is the transport of charge in and outside the cell. Most importantly, the transport of ions. So these are electrically charged particles. And of course, they are much larger than electrons. They're moving inside the battery in an electrolyte shown in blue and basically mimic or define the current that you can extract outside of the cell. Of course, we also have electrons moving inside the cell. They are moving through these cathodes, which are usually porous material. And the reason is that the most important part, which is at the core of every electrochemical cells, are the reactions that take place at these interfaces between electrodes and electrolytes. And the transport of these ions is dominated by many different influences, for example, diffusion, electromagnetation, and convection. In order to be able to solve these on a quantum computer, we used a step-by-step approach in order to solve the whole battery model in the end on the quantum computer. So to give you an overview what we are working with, I want to show you the equations we're working with. So don't be scared. You don't have to understand them fully. Just wanted to show the complexity here. So we have two main coupled equations, which are shown in green. So the concentration balance for the ions and the charge conservation for the electric charge of the ions. And these are influenced by different factors. So we have diffusion, we have electromagnetation, conduction, diffusion current, and convection. And the probably most important part is the generation and consumption, which in battery cells usually happen through reactions. And these are usually nonlinear factors for our differential equations. So they are governed by the so-called Butler-Volmer reactions, which add a lot of complexity to our models. So in order to solve this on a quantum computer, we start off with the simplest case, which is the so-called Fick's law, which is basically just a typical diffusion equation. So here we only look at the ions, which, because we don't look at the potential fields, are not even charged here. So we just have particle motion. And that means we are only left with the concentration gradient. We don't look at the electrolyte potential yet, and we end up with a linear equation. So this was our first test bed for the quantum algorithm. As mentioned, we used the DQC algorithm by Pascal, and we tested this with an initial sign distribution shown in blue here. So you can see the numerical reference as a dotted solution and our predictions with the DQC and solid lines, and we can see that they match quite nicely here. We see some artifacts on the boundaries, which we will also see later, and I will talk a bit more about later. But we found this was a quite good result for the beginning, so this was quite promising. And it was also only using 3 qubits for space and time in order to solve this. Now, in order to add more complexity, we started to add boundary terms. So it's like mimicking the flat electrodes at the outsides, and we have some flux going in and outside, like a very basic modeling of a reaction. And that's also interesting because this can also change total concentration of over time, which is an interesting phenomena to study in quantum computers because we usually have these unitary operators. So it was interesting to see how the quantum algorithm would perform here. And this generation and consumption of ions could, for example, in the battery come from reactions or collocation into the electrodes, or in a fuel cells, for example, a valve that lets in the fuel and then an exhaust pipe where you get rid of your used ions. So if we look at the results here, it's again with 3 qubits in space and time. And what we do here is we start with basically a cold started battery. So we start in an equilibrium state. So this is like taking a cell out of the shelf and everything is in equilibrium. And then we apply the boundary conditions. We see that the approximations are quite good. However, the initial state is not matched quite nicely. And this becomes more clear why this happens if we don't look at these spatial distributions, but at the temporal evolution at specific points in the battery. So what we see here in purple and blue are the boundaries of the battery. And for example, the red and the yellow curve are inner points of the cell. Now, what happens when we apply a flux at the boundary at a equilibrium cell, it takes some time for the flux to reach the center of the battery. So we see that in the beginning, the red and yellow curves stay constant until this motion has evolved throughout the cell. And what we can see is that the algorithm modeled this, let's say, homogeneous movement in the later time steps quite well, but was not able to catch the beginning. And the reason here is that we have these sharp bends in the distributions at the beginning, which means we have high frequency components in the function. And the basic features that are used in these DQC algorithms was at this time a Fourier map. And then, of course, if the frequencies in the Fourier map are not high enough, we're not able to capture these details. So this was a straightforward solution to this is, of course, to increase the frequencies. For example, if we use frequencies that are 8 times higher, which means we only need 3 qubits more, then we can model them much better. So we can already see that even if we only add like very simple boundary conditions, we need larger circuits in order to model them, but we can also see that the results then get quite good. So we were quite happy with this. And we then went on to adding even more complexity. So instead of just having a constant flux at the boundary, we started modeling like a simulated open circuit. So we introduced like a shadow anode and cathode, and then modeled what happens if we apply a voltage or currents in this anode and cathode. How does that translate to the flux at the boundary? So we do not model full reactions yet. We just make more complex boundary conditions, and we translate typical battery operation modes like constant current and constant voltage into fluxes at the boundary. So with this, we can model different typical operation modes for battery cells. For example, changing the charging speed, which is often done when charging cells, or to switch from constant current to constant voltage during the charging of the cell. Now, how this translates to the actually influence on the boundaries, you can see here. So this shows the flux at the boundary. So in blue, we see like the constant flux, which was shown in the example before. Now, if we change the flux, for example, to a lower current at the boundary, then what happens at the temporal evolution at this boundary of the concentration is that instead of having this very smooth decay of the concentration, we have this sharp band at the moment where we change the current. So we have a very sharp band in the temporal evolution of the concentration. And this gets even more sharp if we go to constant voltage, which is shown in green, where we then have an exponentially decaying current at the boundary. Then we have this even sharper change of the distribution in the temporal evolution. And then it was already clear that this would be hard to model with Fourier features, we need quite high frequencies. And Lorenzo already showed in his, or discussed this already in his talk in the first webinar, that including these high frequencies can lead to some very not nice artifacts in the solution. So, but he also presented already a solution for this, which are so-called trainable Fourier frequencies. So what you have to think is that beforehand, we don't know how large the frequencies need to be in our map in order to model it. So what you could do is you could just add more and more frequencies, but you carry on this large bulk of frequencies and intermediate frequencies, and that makes it hard to optimize just because you have so many basis functions. Instead, you make the frequencies of the Fourier features trainable. So you only have a fixed set of frequencies, but these are automatically adapted in order to match distribution. And then we can see that with these trainable Fourier frequencies, we can find quite nice solutions. So this is showing the constant current to constant voltage case. We can also see in the temporal evolution here that these sharp bands are matched quite nicely. So it's not 100% perfect, but it is a quite good result at this stage. Now, at this point, you might wonder, okay, why even use Fourier frequencies if we have these problems with the frequencies? For example, in numeric simulations, what people often use are polynomial feature maps. And the most common one, probably the Chebyshev polynomials. So they are very frequently used in numerical solvers. And they also have the nice property that you can implement them quite efficiently on quantum computers. So we also tested these feature maps. And what we found is that actually these trainable Fourier frequencies often outperform the Chebyshev feature maps. So, which was quite surprising at this stage, but was a nice finding. We saw that Chebyshev is sometimes better, especially in the temporal domain, which makes sense if we have these non-periodic distributions here. And of course, a Fourier feature map is always periodic. But we also saw that the trainable Fourier frequencies are not that far behind. So we didn't see a clear benefit on using the Chebyshev feature maps, at least yet, at the scale of around 6 qubits. So that was a quite interesting finding. So far we see that these trainable Fourier feature maps are actually the strongest feature map we have in this setting. What was also necessary to make this work is some reweighting of the different loss terms. So we have costs working on boundary conditions, costs working on differential equations, and on the initial conditions. Now, what you can, of course, do is weight them differently in the loss function, as you would usually do in optimization of, for example, a neural network. What we also found is that it's very important to use the right number of collocation points. So these are the points where the functions are evaluated during training, and especially the weighting between boundary and interior points was important. And now it makes sense that you need like a decent amount of points, especially on the initial condition, in order for the high frequencies to converge. But we found that we needed much more points than we expected, and it's probable that this is because with more points, you have less error in your gradients. And we found this was important for the initial condition to converge. Now, equipped with these insights, we will now go to like a full battery. So here's the example of a lithium-ion battery. So what we do is we introduce the charge conservation again, which means that we now have to take the potential field phi into account. And of course, because we model the transport of ions, these are charged particles and their movement is coupled to the potential field through this algebraic equation done. And as a consequence, we don't only have to track the temporal evolution of the concentration now, but we have to take into account two more variables which we have to track, which are the potential in the electrolyte and the potential on the electrodes. However, we can set the anode potential as a reference, and then we're only left with one more variable. In general, we would also have to model a second species of ions, which is which would here be a PF6, which is a negative charged ion, and it maintains the electroneutrality of the electrolyte. However, in this case, it's only a shadow variable that is not explicitly modeled, but we still have to account for its influence on these on the constants within the differential equations. In this case, the electrolyte electrode interfaces are still surfaces, so we only have the reactions at the boundary terms. So that's why these inner reaction terms are still grayed out, because we don't look at porous electrodes yet. However, we already use the correct Butler-Volmer equation, so these nonlinear equations, to compute the reaction terms from the potential that is within the cell. So let's look at some preliminary results. So now solving these coupled equations is quite challenging because we have to keep track of different variables. So what we did is we first did some tests with neural networks. So these are physics-informed neural networks, so no quantum backend here. But we can see that we're already able to solve it quite nicely. So it's not perfect yet, but it's some good first result here. And I have to note that we use 3 different networks here for the different variables just to make training easier. So each variable has its own set of parameters. We also did some first tests on encoding the solutions now with a quantum circuit. So this is not training the full, this is not training with the differential equations, but computing a reference solution and then fitting the quantum algorithm or the quantum circuits to produce this solution. We see that we can match the general shape, but there's still some artifacts, especially in the spatial boundaries, but also in the temporal boundaries of the initial condition. So what's now left in this project is to put these two things together and then actually solve these coupled equations with the backend on a quantum computer. Now, to give some outlook of the challenges that are lying ahead, I want to give the example of the lithium-sulfur battery, which also Andreas talked about before in the previous talk. So this is a very interesting cell chemistry because of its high energy density. It's a promising candidate, for example, for aerospace applications. However, as we saw in the talk by Andreas, in this case, the ions are not collocated into the cathode, so they don't move really into the cathode, but they react with sulfur from which the cathode is made, and the reactant is then lithium sulfate, which is Li2S. And this formation of lithium sulfate, of course, changes the volumetric properties inside the battery. So the parts where electrolyte are and where cathode are and where now lithium sulfide are changes. And we additionally have to keep track of these volume changes. So that means that in this setting, we have to track 5 variables now in their temporal evolution when solving this problem. So you can imagine that this increases the complexity of the problem, but we're quite positive that we will be able to also solve this with physics-informed quantum algorithms. So to summarize, we examined the relevant parts of a battery model, and we saw the current results we can achieve there with quantum algorithms. I have to say, so we use the backend of Pascal here. So everything is done with emulated quantum circuits. So we didn't run this on actual hardware, but we ran it on simulated quantum circuits. And we also discussed some strategies to improve the convergence of the DQC's algorithms when we use physics-informed training using differential equations. And as an outlook, so the basic set of equations that we discussed here is suitable for different types of cells. And depending on the cell chemistry that you want to study, these probably can be extended to different scenarios depending on the structure of your algebraic equations that arise in your model. And it's also not unrealistic that we can extend this to 3D simulations or more variables where then the scaling advantage of quantum computers will really come into play. Okay, with this, I'm finished with my talk. Thank you for the attention.